you very much. On the onset of this presentation, before I present before you, I would like to thank the team of conference ICRTMD 2023. Special thanks to Dr. Amrita Mudaji for inviting me to be a keynote speaker here. So my research field is based on the ion accelerator, as she has mentioned in my nice introduction. So let me share my presentation. So I hope it is now visible on the screen, or it might be coming up.
Not yet, ma'am. Yes. Yes. Now it is visible.
Okay. So I belong to Inter-University Accelerator Center. So basically our research institute is accelerator-based institute, and we are using the accelerator for generating the knowledge and enhancing the knowledge of the students who are especially doing the research with the energetic ion beams. This is the main tower of our center, which contains the Pelletron accelerator, and we can have the beam in millions of electron volts of energy from it. I am working as a capacity of scientist at IUAC New Delhi, and I was recently awarded DST Sire Fellow to work at Southern University of Denmark for a period of 4 months with Professor Yogendra Mishra, who yesterday delivered a nice talk on the zinc oxide tetrapods. So a little bit, I will be giving the introduction about the facilities we have in our institute so that the people can actually outreach us. They can come to us and collaborate as a user, because it's a facility which is many costly equipments and state-of-art facilities are there in our institute, which can be utilized for the beautiful research people are doing, like Dr. Rehan was mentioning. So sometimes you can also simulate the results of energetic ion, what they will do on the cells for their apoptosis process and all. So I will give the brief introduction, then I'll tell what is the ion matter interaction. Basically, if you choose the different range of ion energy of the ion beam and how it interacts with the material, and some glimpses of my research work if time permits. So the Inter-University, our institute established in 1984 by then Government of India. It is the first inter-university center of UGC University Grants Commission. And we were able to deliver our first beam as a national user facility on 8 July 1991. The objective of this institute is to give the ion accelerator and the experimental facilities for higher education for the research and PhD students. And we facilitate internationally competitive research environment. So we have users all around India and some users from the top labs in abroad too. So we ask for the proposal twice a year in month of July and December, where you can actually ask for the beam time, and we provide the funding also for the student for 3 years. And we have different kind of outreach programs, like we have master's and bachelor's program where it means not the degree awarding, but they can come to our institute and visit the facilities so that they can get motivation to take up science in their advanced careers and get related to the field of experimental work. Then who all can use the facilities? All the people and researchers who belongs to universities and national institutes of national importance, IITs, etc. And we have the beam from tens of keV to hundreds of millions electron volt. And India, you can see these are the number of users, 900 users from various universities and colleges. And we provide the facilities in the field of nuclear physics, material science, radiation biology, health physics, atomic and molecular spectroscopy, and AMS is accelerator mass spectroscopy for dating purposes. So how ion interact with the material if it falls on a interact with the material. So we can have 3 kind of possibilities when the ion is interacting with the material. It can modify the material through the process of defect production, and it can actually, you can actually use the ion beam to characterize the material, such as Rutherford backscattering and like Pixie and all. and then you can actually deposit the material. By the process of sputtering and all, you can actually deposit the layer on a different variety of substrates to form the thin film, and co-sputter many components to form the multi-component films on a substrate for various applications. So when the ion beam hits the material, it can actually lose the energy of the ion in two processes, through electronic energy losses and through nuclear energy losses. So electronic energy loss are dominate at a very high energy of the ion beam, millions of electron volt, because the ion is moving at a very high velocity. So it is interacting more with the electronic subsystem of the material and do not create much point defects in the system, but actually it creates the zones of amorphization of or crystallization and results in some kind of phase transformation of the material. So some property enhancement can be done using the high energy ion beam. I'm sorry. And in the low energy ion beam, the ion interacts with the atomic nuclei of the atom, of the target atom, because the ion is moving in with the slow velocity, and it has ample of cross-sectional time that it can actually interact with the atomic nuclei, and it can displace it to form the vacancy, and it can actually displace the atom, and it can actually sit somewhere else randomly to create interstitials in between the unit cells. So the crystalline property of the material can be little bit tuned by creating the defects in terms of point defects, vacancies, and interstitials. So you can actually dope or implant the various materials, suppose, for example, silver or any other material which are chemically immiscible sometimes into the target material. And you can actually tune the material property based on your application. So this is the curve of energy loss, where we have x-axis the ion energy and how it is depositing the energy into the material, the energy losses. So you can see at the lower energy, kilo electron volts of energy, nuclear energy loss is dominant, as I explained in the previous slide. And in the higher energy regime, millions of electron volt, electronic energy loss is dominant. And you can do such kind of pretty things at a different energy regimes. And sometimes to get the synergistic effect, you can actually get the beam within this energy regime. So this is our accelerator, which is the 15 million volt unit double peloton accelerator, and it has a multi-ring structure where the potential divider setup is kept, and the maximum voltage is put at the terminal. So just like it's a Van der Graaf accelerator, particle accelerator, where the maximum energy can be 180 million of electron volt. And to boost the energy of these ion beams further, we have a booster superconducting linac through which the peloton output is fed into the linac, and the more energy of the ion beam can be taken, especially for the case of nuclear physics experiments, where they want to see the fission reactions of by dividing the two by dividing a target atom into two unstable nuclei, and find out the time and coincidence spectra of the nuclei to study their property, basic physics properties. Then we have a RBS facility, which is 1.7 million volt Rutherford backscattering facility. By using the ion beam of helium, you can actually find out the composition of the material, suppose with the depth. So we can have like percentage wise, you can know what are the different elements present in the system. Then we have a AMS facility, accelerator mass facility, where we can have the dating profile of the fossils and some rocks which we want to know what is the age of their thing. Then we can do the carbon-14 dating using the accelerator mass spectroscopy. Then we have an indigenously developed accelerator system with 50 kilo electron volt of energies and deliverables. And then we have some low energy ion beam facilities for the implantation purposes, both in the positive and negative ion beams. This is the layout. From here, we produce the ion at kilo electron volt. Then the injector magnet injected in the terminal. This is the terminal where the highest potential is governed. And then it is grounded. So one time it accelerates from here, and one time it accelerates double energy by going to the ground. And then this is the switcher magnet. We can apply the magnetic field accordingly to perform the experiment in different beam lines like radiation biology, atomic physics, etc. So we can perform the experiment in beam hall as per our requirement. So this is just glimpse of what the facilities are in the nuclear physics. We have the Indian National Gamma Array. It's a multi-institute project which was funded by DST. So you can actually take the beam from here and put on, made to fall it on the target, and then you can actually study the gamma rays which are coming out of that, and to find out the properties of the target and incident ion geometry. And we have a NAND setup. This is also a multi-institute facility where many institutes have come together to actually purchase it to perform the experiment for neutron detections and lifetime, etc. This is for the recoil. This is another nuclear physics technique. So I'll be going a little, this is a control room from where the beam tuning is done, because these are all higher energetic ion beam and they produce the radiation when they move very fast. So everything is done from the control room. And this is the layout. All the beam lines are separated from one place to another by thick lead block, so that one person is doing experiment here. It will not allow the other person to get interacted with the radiation. So in the material science facilities, we have like in situ facility XRD. We have integrated in the beamline because we want to see what kind of phase changes are happening when we are irradiating the sample. And because XRD is the technique which can actually tell you the phases, about the phases of the material. That is why we have integrated it with the beamline, and it can be used as a standalone technique also, offline also. Then we have a Raman also, which is in situ in the beamline. And just where we have various microscopes. If somebody is interested, kindly write a proposal, send to us. So you all will be able to use the facility of IUAC once you become the user of it. And there we have various deposition, thin film deposition technique and annealing furnaces. So let us come to the research area. So I'll be discussing few of the research with you. So as we know that when we see the lotus leaves, it has a very nice hydrophobicity, and because all the time the leaves are submerged in the water, but still you can see that the droplets are always floating, which is because it has what is the reason for it? Because it has a coating of nano material over it, nanoparticles over it, which do not let the water seep into the leaves and avoid the degradation of the leaves. So this is how the water is actually making a shape of a ball. So it is not actually letting the leaf surface wet, but it actually floats over it because of the presence of the nanoparticle. These surfaces are therefore known as the hydrophobic surfaces. So to get after getting the idea from the nature, we actually thought that such hydrophobic surfaces are having lot of applications, like in the self-cleaning and in the water-resistant paints. So we can actually perform these kind of fabricate these kind of nanoparticles on any material using the ion beam, and tune the contact angle of any material. So we performed one experiment in the low energy ion beam facility at 90-degree beam line, and we irradiated indium phosphide. So you can see this is a pristine film with no sign of dot formation. And as we are irradiating with 2 into the power 10 to the power 16 ions, some dot formation started appearing on the surface. And as we are increasing the fluence, these dots are getting narrow in size, means narrow size distribution. And you can see that when we did the SEM measurement with EDX, we can see that at first the ratio of indium to phosphorus was 1:1. But as we are irradiating with ion beam, phosphorus being the lighter element is getting preferentially sputtered, and the surface becomes indium rich. And then we calculated the contact angle of these surfaces because we have nice dots here. So we were able to tune the contact angle of the surface up to 110 degree. You can see this profile. And the formalism for this why these hydrophilic or hydrophobic surfaces are formed on a material, it is explained by Casey-Baxter formalism, because basically the air trapped between the nanodots do not let the water seep into the nanodots when they attain a certain size. This result you can find in these papers. In the second, we have made a composite of hematite and Nafion polymer for the cholesterol biosensing. So we form the composite using the chemical routes, and we scan the surface using the scanning electron microscope. You can see that the beautiful nano rods are formed on the surface. So nano rods have special geometry, and the active surface area is more than the dots. So it actually interact more with the interactive sensing molecules which we want to sense. And we confirmed this further with the AFM, which also can complement the finding of SCM. And then we did the cyclic voltammetry measurements of these composite for the sensing of cholesterol enzyme, cholesterol enzyme, cholesterol using the cholesterol enzyme. So it is basically an enzymatic sensor. And we did the selectivity studies because our blood contains a lot of things apart from cholesterol, like urea, ascorbic acid, citric acid, etc. So we need to show that it is selective to the cholesterol. So we did the selectivity studies, and it clearly shows the selectivity for cholesterol. And then we calculated the contact angle for this also. So our initial sample was having 98.8 degree contact angle, but as we have activated this with cholesterol enzyme, then the surface contact angle becomes hydrophilic in nature, which is actually the requirement of the sensor, because as it needs to sense, it has to actually absorb the molecule to get the efficient sensing. And then we did the stability test of these electrodes, and we could find that when they are contained in the refrigeration condition, they are stable up to 8 weeks, and then they start degrading. So our enzyme sensor was selective to cholesterol, and the mechanism is given here. The more details you can find from this paper. In the second study, as our center is ion beam accelerator center, so it is important to find out what is the radiation shielding material we can use. And sometimes in the nuclear reactors also, such kind of studies are very significant. So on the alumina, we did some irradiation measurements, and you can see that as we are irradiating, the XRD peaks becomes means lower in intensity. So crystallinity is decreasing, and it is little bit shifting to little bit phase changes there. That shows that it is actually making some impact over it. And then you can see that the PL spectra, the intensity also reducing. So PL exhibit two strong emission bands around 679 and 695 nanometer due to the chromium impurities present in the alumina. So it provides good support to the XRD results. And then we did some SCM and AFM, and you can see that because they are very rough samples, so they are like they can be used as the shielding material also for the reactors. And then we did some theoretical calculations, and the details I will not go into. So we have found out that per ion, the track radius is around 2.6. The area which is affected by the ion beam is around 2.6 nanometer. So these are the conclusion. Findings can be found in these papers. So in the work which I am carrying out in the SDU, I carried out at SDU is, I will not go into the details of how these tetrapods are formed because Professor Mishra nicely explained it yesterday, but you know that at a very high temperature, anything will burn into ashes, and these ashes are actually important to find out their properties. So if we heat zinc plus PBV in a certain ratio and heat them at 900 degree, then white color powder is formed, which is actually in the form of a tetrapod. Why is it is in the form of a tetrapod? Because zinc oxide is a wood-side structure, and the natural geometry is of tetrapod. So you know that you can see that this crucible was kept with the powder and it is heated, so it is this color, and then this powder is again, this is a tetrapod powder, and the same characterization was performed. So the beauty of this product is material is that because it is having 3D geometry, so they are not agglomerated, but they are forming porous geometry within the material. This porosity is actually can be used for various applications, like for sensing, catalysis, for biomedical applications, because you need to have the porosity to get the maximum surface area to the interacting agent. This is the more magnified image of these tetrapods. So you can actually make a contact of these two electrodes if you form it on a particular electrode, and you can do the sensing measurements over it. And this is the like when you are increasing the UV light exposure, that time it is going up, and when you are removing the UV, it is going down. So this application shows that it is UV sensitive, and that can be used for the sensing applications. Because of these areas, every leg is acting as a carbon, means as a rod, sorry, not carbon, zinc oxide nanorod, and because of these active areas, the particles of sensing gas is actually interacting with these rods individually, and they are giving us a response, good response. So they have multiple applications, and these are the findings of Professor Mishra's group. And so getting motivation from this, we have actually make a composite of PEG with the zinc oxide tetrapod and catalysis to use as a catalysis. And catalysis is a process where the material itself do not get consumed, but it actually add the value to the reaction, and it makes it fast. And so this is what we did. Zinc oxide tetrapod plus polyethylene glycol we have taken, and we have formed the proper well-dispersed solution using probe chromication, and spin coated the samples in the form of thin films. Why? Because they have the porous geometry, and PEG bind with the tetrapod legs, and they show the efficient catalysis. These are the same result. This is for the polymer in the magnified images. Then this is tetrapod, and when we are mixing, the polymer is getting coated over the tetrapod. We actually confirm this this tapping of the tetrapod legs with the helium ion microscopy also. So you can see one leg, it is coated completely with PEG. And then we did some Raman measurements over it. We did in the confocal mode. So this is the region where we perform the confocal. And you can see this blue color is the zinc oxide tetrapod, and this red color is the PEG. And when we did the individual mapping, we can see actually the whole sample is having the composite arrangement within the sample, and we could find out the peaks in the regime of 200 to 1350 Raman wave numbers. And these are the deconvoluted image. So clearly it is showing the zinc oxide presence and PEG presence, molecular bands presence. And then we did the UV absorption. So because of the hydrogen bonding between the ZNO and PEG, it is little bit shifted towards the low energy, indicating the binding of PEG over ZNO. These are the modes which are present over functional groups which are present in the sample. And we did the UV absorption spectroscopy, and it is clean spectra except the peaks corresponding to the ZNO and PEG. And then we did the experiment to use the electrodes as the degradation of organic dye molecules. So you can see we use the methylene blue dye, and this is a 0 minutes exposure time to UV. Both the materials are UV sensitive, so as we are exposing them to the UV, they are generating electrons, and we have to arrest the electron hole recombination. So we that this PEG actually acts as a barrier to make them recombine. And then as we are increasing the UV exposure time to these dye molecules, you can see the intensity of the absorption going down, which indicates that the methylene blue dye is completely getting degraded. So summary of the result is explained in this. The mechanism is that ZNO, when it is exposed to the light, it is generating electron and hole pairs. Similarly, PEG also UV sensitive. So this is combining with O2, activating the oxygen molecule, and in the oxidation reaction, this H plus is interacting with the methylene blue dye molecule, bringing out the OH hydroxyl group, activating them, and thus the methylene blue dye is decomposing into CO2 plus H2O. So the organic pollutants are actually breaking into the more sustainable material, which are not that much harmful to the water. So we are actually doing the wastewater management. Thus, we are actually doing the environmental remediation. So this is the methylene blue dye, and after the degradation, the color has lost. So recently we have communicated this paper. So let's hope for the best. I have able to communicate that zinc oxide tetrapods are having quite a lot of applications. And I'm thankful to the DST SCRB for the SIRE fellowship and giving me opportunity to work in Professor Mishra's group. And I am thankful to Professor A.C. Pandeyji, Director of IUSC, Professor Hos Gungar, Director of MCI, Yogendra, Head of Smart Material Group, all the colleagues at MCI, Dr. Manjeet and Manjeet Goyar, and all the colleagues at IUSC. Special thanks to the organizer of ICRTMD. This is our small group at SDU. This is Professor Mishra, me, Manjeet, and other people. Thank you very much. This ends my talk.